Good afternoon. My name is Marie Rienzo, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions to the webinar by clicking on the question mark in the WebEx toolbar. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih/mindthegap, in approximately 1 week. You'll receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meetings, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and the Director of the Office of Disease Prevention.
Thank you, Marie. Today's speaker is Dr. David P. McKinnon. Dr. McKinnon has been developing, evaluating, and applying methods to assess how interventions work for over 30 years. He's a foundation professor of psychology at Arizona State University. He received his undergraduate degree from Harvard University and his PhD in measurement and psychometrics from UCLA in 1986. In 2011, he received the Nan Tobler Award from the Society for Prevention Research for his book on statistical mediation analysis. Dr. McKinnon has been principal investigator on several NIH grants. He received the Merit Research in Time Award from NIDA for his research on mediation analysis. He is a fellow of the Association for Psychological Science, Society for Prevention Research, the American Psychological Association Quantitative and Qualitative Methods Division. He's past president of the American Psychological Association Division 5 and is president-elect of the Society for Multivariate Experimental Psychology. It is my great pleasure to welcome Dr. David McKinnon.
Thank you, David, for the introduction and also asking me to give this talk. And thank all of you out there for coming online for the talk. I'm sitting in my office at Arizona State University. I could be the only person. For some reason, I'm not able to continue the slides here. Let's see. There we go. I'm here. I could be the only person in my office here at Arizona State University. I'd like to thank NIDA for their support over the years for this research. In 2016, I gave a Mind the Gap presentation on mediation analysis that described sort of why you'd want to do it and then the different models that could be applied, including longitudinal models and multiple mediator models and so on. This talk, I have some of the same motivating slides, but I'm going to focus on the single mediator model with the goal of comparing traditional mediation analysis with causal mediation analysis. So I'll start with some examples and motivations, describe traditional mediation analysis, and then causal mediation analysis. And then I'll show the links between the two and future directions. So the goal of this is conceptual. It's to help provide links between the traditional and causal mediation analysis methods. These causal mediation analysis methods are more general. A lot of this talk is from an article just published in Prevention Science, listed below there. I'd like to thank Matt Valente and Oscar Gonzalez for their work on that. Also, I have a slide of donuts that Matt Valente made. I'll show you those a little bit later. There's my website. And then a lot of the material in this talk will be covered in the second edition of my mediation book. A mediator is a variable that's intermediate in the causal process, relating an independent variable to a dependent variable. Here are some examples. A tobacco prevention program promotes anti-tobacco norms, which reduces tobacco use. Neglect, abuse in childhood leads to impaired threat appraisal, which leads to aggressive behavior in adolescence. For each of these examples, the mediator is written in bold. Screening program increases identification of early stage cancer, which reduces cancer deaths. Wellbutrin increases participants' willingness to quit and self-efficacy, which are associated with 1 month abstinence from tobacco. that last example has two mediators. It has willingness to quit and self-efficacy. And probably you have some examples yourself of mediating variables. Here's the single mediator model written in the traditional method with boxes for variables. We have an independent variable that causes a dependent variable. It has a direct effect, x on y, and then it has this indirect effect through m. And the coefficients a, b, and c prime are the typical notation used in the social science literature. This is a directed acyclic graph, which is more common in the causal literature, where again the arrows represent the direction of causality and dots represent variables. Here's some more mediator definitions. Mediator is a variable in a chain whereby an independent variable causes the mediator, which in turn causes the outcome. It's the generative mechanism through which the focal independent variable is able to influence the dependent variable. And then my favorite definition is this last one. It's in an epidemiology dictionary. A mediator is a variable that occurs in a causal pathway from an independent variable to a dependent variable. It causes variation in the dependent variable and itself is caused to vary by the independent variable. And this is the challenge of analyzing mediating variables. They're both an independent variable and a dependent variable at the same time. Most of statistics focuses on the relationships between two variables. With two variables, there's a limited number of relations. We have x causes y causes x. X and y are reciprocally related. We have measures of these effects, including the correlation coefficient, regression coefficient, covariance odds ratio, and so on. With three variables, there's a lot more options. X to m to y, x to y to m, y to x to m. And we have special names for these third variable effects. One of those names is mediator. Another type of third variable effect is confounder or collider. With four variables, we have lots of possible relations, x to z to m to y to m to z to x, and so on. And with five variables, there's so many combinations, it's probably better just to go home and take a nap. But we don't take a nap because lots of behaviors, especially health behaviors, have lots of variables involved. And typically what we'll do is we'll try to randomize something, or we'll focus on a smaller version of this more complicated model. For example, we'll focus on the mediation part or some other part to try to make some progress in understanding these dependent variables. Mediation is one of three possible third variable effects. Where here I've written T for third variable. Number one, you'll see that X causes T, which then causes Y. It's a mediator. We have a T that's a confounder, where the confounder is a cause of both X and Y. And then we have the case where X and Y causes the third variable, called a collider. And these are the three possible third variable effects. In these models, an interaction, for example, or moderator would be considered a nonlinear effect. So these directed acyclic graphs represent the relationship for linear and nonlinear models. This next slide, to be more realistic, I've added the x to y relation. So again, the mediator, we have x to the third variable, which is a mediator to y, and then there's still a direct effect left over. Mediator is the focus of this whole talk. We've got a confounder, which is a cause of both x and y. And if we want to get the correct estimate of the relationship between x and y, we'll want to adjust for that confounder. If we don't adjust for that confounder, we'll get a biased relation between x and y. And then finally, a collider. We have x and y cause the collider, and we should not adjust for the collider. If we want the right relation between x and y, we should not adjust for it. Collider variables, I think, are one of the most helpful parts of modern causal inference because they've made it clear that there's this type of third variable effect. So mediation will also have confounders and colliders involved, but we'll focus on mediation in this talk. Again, these models are non-parametric, and moderators or interactions are treated as nonlinear relationships. Another type of variable is a covariate, which is generally all of these. But generally, a covariate is a variable that doesn't have a substantial effect on x and y when it's included in the analysis. So mediation is important in many fields because it addresses central questions about mediating processes. It's important for basic research on mechanisms of effects. It's critical for applied research, especially prevention and treatment, to identify critical ingredients leading to more efficient interventions. And this is how I became interested in mediation analysis, when we wanted to know how it was this tobacco prevention program achieved its effects. Several agencies in NIH are interested in mediation analysis. For example, the Science of Behavior Change Initiatives focuses on mediating variables that lead to treatment and so on. And of course, there's a lot of interesting statistical and mathematical issues involved in mediation analysis. A ubiquitous theory in psychology and other areas is the stimulus-organism response theory. The idea is that you have a stimulus. Say I ask you to multiply 24 and 16, and we have a response, your answer 384. The organism, that's you, is in between the stimulus and response, and would like to know what the mechanisms are that translate that stimulus to a response. This is similar to the organism as a black box where we have an input and output, and then we try to understand what's going on inside the black box. Here's the diagram of that. So we have a stimulus and response, and we think there are mental and other processes that occur in between the stimulus and the response. And we can measure that stimulus accurately, and we can measure the response accurately, but the challenge is to measure the mediating variable. I like to bring up this SOR theory because it demonstrates some of the challenges with mediation analysis. First of all, the mediating process is usually unobservable. We'll have to come up with some way to measure that process. And you could argue that mediation, in fact, is really a measurement problem where progress is made as we measure that mediator more accurately. The SOR model demonstrates that this process can occur at different levels, at individual level, neuron level, team level, atom level, cell level, state level, and so on, and that the mediating processes can all be happening simultaneously. And finally, the mediating process may be part of a long chain. The researcher needs to decide what part of the long mediation chain to study. This has been called the micromediational chain. There are two main motivations for mediation analysis. One of them is older, from around the 1950s. That's mediation for explanation, though it's still applied today. The idea is there's an observed relationship, and then you try to explain it by adding a third variable. You see how that relationship changes to decide, to learn more about that relationship, and also to understand how third variables affect that relation. And there's some of the names in this literature: replication, explanation, intervening, and specification. And there's sort of what they match with today. Replication would be a covariate, explanation would be a confounder, intervening would be a mediator, specification variable would be a moderator. Not much evidence of collider variables in that literature. So this mediation for explanation focuses on an observed relationship, and then you try to understand why it occurred. More modern application of mediation is mediation by design, where mediating variables are selected because they're causally related to an outcome variable, either from theory or empirical research. An intervention is designed to change the mediators. If the mediators are causally related to the outcome, then an intervention that changes the mediator will change the outcome. This approach is common in applied research like prevention and treatment. So in a diagram here, you'll notice I've added M1, M2, M3 to indicate that there can be more than one mediator addressed. We have an intervention program, and there's a theory called manipulation or action theory. That's the theory that provides the basis of what actions you'll have in your intervention that are designed to change the mediator. And then we also have conceptual theory for how which mediators or risk factors are related to the outcome, which is more like traditional theory that looks at what are the predictors of an outcome variable, for example. So mediation actually has two theories: a manipulation theory for how the intervention will change the mediator, and then conceptual theory for which mediators are causally related to the outcome. So one way to think about mediation analysis is maybe a little bit simpler than grand causal approaches. Let's say you have a measure of X and Y, and then you add a measure of M. What's the best way to use that information? You'd have to agree that means there is more more information, right? Because now you have a measure of M. But what's the best way to use that measure of the hypothetical mediating process to increase information from a research study? Traditional mediation analysis has 3 regression equations, and we'll use these actually in the causal mediation later. And tests for mediation use information from some or all of the equations. The coefficients could be estimated with ordinary least squares, covariance structure analysis, logistic regression, survival analysis, and so on. Here in this talk, we'll focus on ordinary least squares regression. Here's the most important test in any research study when X is an intervention, and this is whether the intervention changed the outcome variable, that C coefficient. And if there's randomization to levels of X, then the C coefficient with some assumptions will have an interpretation as a causal effect. Another test would look at the effect of X on the mediator, and again, if X is randomized, that A coefficient can be interpreted as a causal effect. In this third equation, we have both X and M predicting Y. Note that in the regression equation, there's actually a covariance between X and M. It's just not drawn here. But in this situation, neither B nor C prime have a clear interpretation as a causal effect unless some assumptions are satisfied. So we have the Y variable predicted by X and M. Later on in this talk, I'll add an interaction, which will be represented by the H coefficient, the interaction of X and M on Y. And the interaction will reflect the extent to which the relation between M and Y is different across levels of X. Mediated effect measures can be the product of A times B, also C minus C prime. Generally, the C minus C prime may be more intuitive to understand, where C is the overall relation between X and Y, and C prime is the relation between X and Y adjusted for the mediator. So it seems to make sense, right, that the difference between them would be the mediated effect. With continuous data, and for the example in this talk, with continuous M and Y, the product of coefficients AB estimator will equal the difference in coefficients estimator. We also have the direct effect, C prime, and the total effect, which is just the sum of the mediated effect and the direct effect. By the way, the words indirect effect and mediated effect are used synonymously in this presentation. Later on, when we talk about the causal effects, they'll be called indirect effects. But again, we'll treat those as meaning the same thing. So we have a mediated effect that we could estimate. We can also estimate a standard error of that mediated effect, which is derived using the multivariate delta method. We could divide that mediated effect by its standard error and get a critical ratio. Here I've got a Z prime. But it turns out that the mediated effect divided by that standard error does not always have a normal distribution, and we can get more accurate significance tests and confidence intervals if we accommodate the fact that A times B doesn't have a normal distribution. It has a distribution of the product. So we can use methods based on that distribution of the product, or methods based on resampling to get more accurate significance tests and confidence level interval estimation. So in general, in most models, the AB coefficient is by far the most general approach to testing for mediation. Best methods for confidence limit estimation and significance testing use the distribution of the product or the bootstrap. Another good significance test that won't produce confidence limits is the joint significance test. And that would be just testing whether the A path is statistically significant and the B path is statistically significant. For these methods to work, there are assumptions. To estimate C minus C prime, we'll need equations 1 and 3, but we'll mainly focus here on equations 2 and 3 for the A times B estimator of the mediated effect. We assume we've got reliable and valid measures of the constructs we think we're measuring. We assume the coefficients reflect true causal relations in the correct functional form. Usually the functional form is linear, although that's not necessary. So primarily we're assuming we have no omitted influences. We assume the mediation chain is correct, that X causes M and M causes Y. And we assume that there are homogeneous effects across subgroups, that we don't have any subgroups of people where the X to M relation is different or the M to Y relation is different. Like I said, later on we'll add the XM interaction, which allows for an interaction effect. And again, the XM interaction and the prediction of Y will test whether the relation of M to Y differs across levels of X. So how is causal inference usually treated in traditional mediation analysis? Again, it's with those assumptions of true causal relations and no omitted variables. It's been noted there's a challenge with mediation analysis because M is not randomly assigned, but it's self-selected. One option would be to measure all the relevant variables, include them in the analysis. In fact, Blaylock's presidential address suggested that sociological phenomenon had about 50 variables, so the idea would be to measure all 50 of those variables. It's interesting to think about how many variables are relevant for your research, and most prevention outcomes and behaviors and so on often have lots of variables that are relevant. But the main way that causal inference is addressed in traditional mediation analysis is the consideration of threats to external and internal validity in the tradition of Shadish, Cook, and Campbell, more like writing an argument or considering the different threats and whether and how valid they are as part of a research program. So now we've got modern causal inference. Causal inference is the process of drawing a conclusion about a causal relation based on the conditions for the occurrence of a causal effect. So instead of measuring associations here, we'll have some conditions that'll be consistent with the causal effect occurring, and we'll test whether those conditions occur. It differs from association inference, like in regression we just talked about, in that causal inference analyzes the response of the effect variable when the cause is changed. So it's a different approach than the traditional analysis. Here's a few quotes. The first two quotes are from an excellent book on modern causal inference by Morgan and Winship. More has been learned about causal inference in the last few decades than the sum total of everything that had been learned about it in all prior recorded history. The use of counterfactuals for causal inference has brought clarity to our reasoning about causality. And the causal revolution did not happen in a vacuum. It has a mathematical secret, a calculus of causation, which answers some of the hardest problems ever asked about cause-effect relationships. So these are quotes by Gary King, Tyler Vanderweel, and Judea Pearl. Most of these modern causal inference approaches are based on a counterfactual or potential outcomes framework. In these models, all the possible counterfactual and actual conditions of an experiment are considered, and the statistical model is based on all of these potential outcomes or potential conditions. It requires consideration of conditions that did not occur and even conditions that could not occur. Here are some donuts. Mainly I bring up the donuts so the next time you see a donut, you'll think of potential outcomes. Because if I had a couple donuts right now, maybe I'd have more energy. We do this counterfactual thinking all the time. It's important. It's often how we make decisions. We do counterfactual thinking after an event occurs. We do counterfactual thinking before an event occurs. It's the consideration of possible actions besides the action that was actually taken. For example, if I went to the University of Barcelona instead of UCLA for graduate school, I would be fluent in Spanish. So these counterfactual thinking is not unusual. What if we developed a whole statistical method based on this type of counterfactual or potential outcomes thinking? And that's the point of modern causal inference. Why not clearly state causal effects and address assumptions with methods that are developed for causal inference? We are in a causal revolution. There's some citations there. It's a very active area of research. For mediation, it's especially active. There's two excellent books that have come out, Hong in 2015 and Vanderweel also in 2015. Epidemiology, medicine, and public health have been relatively quick to adopt these new approaches, but it's rare to find these methods in psychology and other fields, although there are some exceptions. So what is it? Let's start with the case of one participant and two groups. What we'd like to have is an individual causal effect for that person, where I represents the participant here. We'd like to have their score if they're in the treatment, which I represent 1 as treatment and 0 as control, and would like to have their score in control, and would like to have it at the same time. Would like to have that subject in both conditions at the same time. The causal effect is the difference between that person's score when the participant is in both conditions at the same time. But we usually can't have the same subject in both conditions at the same time. So below in red, I've written these impossible potential outcomes. We usually only have the y-score for that participant in treatment, and then a counterfactual and control, or we have the y-score and control, but we need that y-score in treatment. So red is the counterfactual situation, and we won't be able to have that. So to make it a little bit more concrete, here's data from 8 people. Their assignment, 0 is control, 1 is treatment. Their observed y-score, I've just left this as binary, either 0 or 1. So for the first 4 subjects who are in the control group, their potential outcome in the control group is the actual score that they got. But we don't have their potential outcome in the treatment group. Similarly, for the last 4 subjects in the treatment group, we have their scores for the potential outcome if they were in the treatment, but we don't have their score for their potential outcome in the control group. This is called the fundamental problem of causal inference, that you can't have all participants realistically serve in all conditions at the same time. But there's a solution to this, and that's to randomly assign units to conditions and use the average in each condition as the counterfactual for the other condition. And we'll calculate an ACE, or average causal effect, by comparing the means in the treatment group to the mean in the control group. And below there you'll see an E that refers to expectations. That's another way to write, to get the mean in the treatment group minus the mean in the control group. So the randomizing solves this fundamental problem of causal inference. Of course, there are assumptions that are necessary for this also. The most intuitive one, I think, is exchangeability. You have to assume that by randomization, you have the people in each group are the same. They're exchangeable. And then also some assumptions about the treatment, that there's not something about the treatment that spills over across individuals. So someone's condition would affect someone else's condition. And assume also that there's only one version of the treatment. There's not a lot of different versions of the treatment. So that's the case with an X and a Y variable. Now we need to find a way to add a mediator. And one of the ways that'll help with that is we'll make a distinction between the value of a variable and the variable itself. And we'll use a lowercase letter to represent the value of the variable and an uppercase letter to represent the variable. Again, we'll use x equals 0 for control and x equals 1 for treatment. So y is the value of the variable y, or capital Y. The capital letter is the variable and lowercase letter is the value of the variable. And again, I codes participant. Remember, there were 2 potential outcomes in the 2-group design. In this design, there are 4 potential outcomes. And let's start at the upper left here. We have the score for this individual. The first number here represents X, so this would be the control group. And this represents the mediator value in the control group. So it's the participant's Y value in the control group setting the mediator value to the value would have been in the control group. And we'll actually be able to measure this, right? Because for participants who are in the control group, we'll have their mediator value in the control group. In the second one, we have the Y value in the treatment group at a mediator value in the treatment group. And again, we'll be able to measure this because the subjects who are in the treatment group will have their measure of their mediator value in the treatment group. These next 2 potential outcomes are in red because they're impossible to observe. This would be the y-score for that person in the control group, but at their mediator value if instead they were in the treatment group. And this next one will be the y-score in the treatment group, but for their mediator value if they were in the control group. So the first symbol here represents X. The second symbol represents the value of the mediator. 2 of these are potentially observable, and these 2 in red we won't be able to because they are the condition that they're assigned is different than the mediator value condition. But once we have these, again, still talking about individual causal effects, we have what's called the total natural indirect effect and the pure natural indirect effect. This is using names in Villery and Vanderweel paper, where we have the total natural indirect effect, that's the mediated effect in the treatment group. We'll compare the person's Y-score, keeping the treatment group the same, but moving from a mediator value in the treatment group to the mediator value in the control group. So we're turning the mediator value on and off and comparing the Y-score after doing that. The definition of the pure natural indirect effect, which would be the indirect effect in the control group, again, this time we'll keep the X condition, in this case control, and we'll turn on the mediator and compare that to turning off the mediator. And when we compare those, and again, this is still for individuals, we'll get a measure of the natural indirect effects. The pure natural effect, direct effects, are analogous, but now we keep the mediator value the same in control and go from treatment to control. And here we compute the mediator value in treatment and move from and changing treatment to control. And these last two, this is the control direct effect. This would be the Y-score in treatment at a certain value, M of the mediator, compared to the Y-score at a certain value at this same value of the mediator in the control group. And then this should look very familiar. This is very familiar. This is the difference between, this is the same way that we'd estimate in the two-group design. This is just taking the Y-score in treatment minus Y-score in control. A mnemonic, the T refers to the treatment group and P refers to control group. We can take, just like we had average effects in the two-group design, we can get average effects in this as well. So what we'll compare the average of score, Y-score in the treatment group for someone with a mediator value in the treatment, and we'll subtract the expected value for that in the treatment group again, but again, switching the mediator on to off. And similarly, the pure natural indirect effect will keep it in the control group, but again, switching the mediator on to off. And the pure natural direct effect, again, will keep the mediator the same, but switch the treatment on to off. And then here we've got the mediator value in the treatment group switching treatment to control. And then these will be the expected values to calculate the other quantities. It's not possible to observe those two red expected values or potential outcomes. What we'll do is we'll predict those based on what we observed and about the treatment and control groups and also assumptions. And we'll often use regression models to do that. These equations for those potential outcomes apply to continuous data, binary data. They're general and non-parametric. When we go ahead and compute regression analyses that we'll use to compute these expected values, they'll come from a variety of different types of regression analysis. Starting with the total effect, this is the same thing in the two-group design. We have an expected value of treatment minus expected value of control. Controlled direct effect will have expected value in treatment at a specific value of the mediator subtracted by the value at the same value of the mediator but in control. It's difficult to select the value of M. Here we've just picked an M. One way to do that would be to pick a value of M that the participant would naturally have, rather than fixing it to a certain number. And we'll end up using these natural ways to specify the mediator value to compute the direct and indirect effects. So for example, the direct effect in this comparison here, again, turning the treatment from on to off, but keeping the mediator value at control. It's the effect of treatment setting the mediator value to the value that would have been obtained in the control condition. So we'll end up taking the mediator value in the control condition for both of these. And then for the treatment group here, we'll end up taking the mediator value in the treatment group for these two estimators of the total natural direct effect. And then finally, the natural indirect effects will fix the treatment at the treatment group at 1, and then we'll again compare the mediator on to mediator off. So we'll have the expected value for Y in the treatment group, but at the mediator value in the treatment group, and we'll subtract the expected value for Y in the treatment group, but at the mediator value in control group. and we'll pick these values for those mediators based on what people would naturally have, and our best guess of that will be the actual means for the mediator in treatment and control with actual data. And again, the pure natural indirect effect is the same idea, but now we're holding the treatment to control group and we're turning the mediator on and then off. So now we're back to these three mediation equations. We've added this XM interaction here. And what we're going to do is we're going to predict those potential outcomes by plugging in, by calculating what Y is with this equation. And then we'll plug in the value for the mediator that we get wherever you see M here. So that way we'll get those predicted Ys for different values of the mediators, for example, the mediator in control and mediator in treatment. So the expected value for the control group at the value of the mediator in the treatment group, again, this is the expected value of Y, the control group for the mediator value in the treatment group. This is just that second equation written out, and I've plugged in the formula for the mediator wherever you see M here, and it ends up equaling the intercept in that second equation plus B times the intercept in the third equation plus B times A. Use the same algebra to get this expected value for Y in the control group for the mediator value in the control group, and we get I2 plus BI3. The pure natural indirect effect subtracts those two quantities, and lo and behold, it gives you that product of coefficients. So the pure natural indirect effect is equal to A times B. We can do the same thing for the total natural indirect effect. Again, so this would be the expected value for Y in the treatment group at a mediator value in the treatment group. And you'll notice that when I plugged in the value for M here, it assumes that X equals 1. So that's the mediator value in the treatment group. And we get this longish formula here. Do the same thing for the other potential outcome. Expected value of the potential outcome will have a Y-score of treatment for the mediator value in control. But you'll notice here, I've specified to get the predicted M value that it's in the control group. We contrast those two and we get AB plus HA. So that's the product of coefficients plus the interaction coefficient times the A path. If we do that for all of these quantities, we'll end up getting the total natural indirect effect will equal AB plus AH. The pure natural indirect effect will equal AB. The pure natural direct effect will equal C prime plus HI, the intercept in equation 3. That's the mediator equation, and so on. It turns out if we ran a traditional mediation analysis and we found an interaction, we would test contrasts, and it'll turn out that this total natural indirect effect will be the same as what's been called the simple mediated effect in the treatment group. The pure natural indirect effect will be the simple mediated effect in the control group. So in traditional analysis, you get the exact same formula for these quantities. The natural direct effects would be the same as simple direct effects in control group and simple direct effect in treatment group. The assumptions for this all to work are no unmeasured confounders of X to Y, no unmeasured confounders of X to M. And if we randomize X and it's successful, we've taken care of those first two assumptions. These last two assumptions, randomization does not take care of those. We assume there's no unmeasured confounders of M to Y. And we assume that there's no effect of X that affects a variable that then changes M to Y, that confounds M to Y. So there's no effect of X that confounds the M to Y relation. These last two will have to do some sensitivity analyses or do some alternative methods to address the extent to which those last two assumptions are accurate. It turns out if the H coefficient is 0, that's the interaction is 0, that AB is equal to both of the causal indirect effects, and C prime, the direct effect from traditional analysis, is equal to the direct effects. So, and this is with continuous M and Y, the mediated effect in traditional analysis will be the same as in the causal analysis, and so the direct effects. If H is not equal to 0, there's a correspondence such that the simple mediated effect for the control group is the pure natural indirect effect and the simple mediated effect for the treatment group is the total natural indirect effect. So although the estimates are the same, the interpretation of results differ between potential outcomes and traditional analyses. The traditional analysis interpretation is a description or associations of variables, description of effects in the two groups. The potential outcomes interpretation is if all persons were in the control group, these are the effects you'd get. And if all persons were in the treatment condition, these are the effects that you'd get. And if all relevant confounders have been taken into account and the assumptions are met, then the traditional simple effects correspond to these causal effects. And again, this is in simple linear models with a continuous M and a continuous Y. Future directions in this research area, the causal mediation methods are ideal for nonlinear models like logistic regression. The traditional analysis with a binary Y and continuous M will get the indirect effects correct, but the direct effects will be wrong. If all three are categorical, then these causal methods are more accurate than traditional methods. These methods are ideal for survival analysis and also from some longitudinal applications. And for all of these, the causal effects are defined in the same way. They're defined as those contrasts between potential outcomes. And we'll do our best to get some prediction of those potential outcomes and contrast them in order to get estimates of effects. Recent work focuses on extending causal mediation models for more than two groups, more than one mediator, for path models, for longitudinal models, methods to deal with having post-treatment confounders. That assumption, remember that there's no effect of X that confounds M to Y. Bayesian methods and also methods that incorporate measurement of X and Y and also causal effects. So there's a lot more to come. So in summary, potential outcomes mediation models consider all conditions, even conditions in which the participant did not serve. When there's no XM interaction with continuous M and Y, traditional and counterfactual mediation models give equivalent estimates, but different interpretations. When the XM interaction is non-zero, there's different interpretations also, but the two methods give equivalent estimates. In particular, the causal estimates refer to simple effects in a traditional analysis. Causal methods are based on a mathematics of cause, so they're a general approach to mediation, and there's a lot more to come. The main reason that I gave this talk was to show how traditional and causal methods are related, so that researchers will become more comfortable, more familiar with causal methods, because at least in the case where M and Y is continuous, they give the same answers. Thank you. And here's a list of collaborators.
Thank you, David, very much for a terrific presentation. You've had a very large audience, and they have been very active in asking questions. So I'll preface starting the questions by saying we're not going to get through them all. We can send you questions that we don't get today, and if you will indulge us and send us brief answers, we will post all of that on the ODP website next week when we post your talk. So let's start with a couple of general questions. You've been writing about mediation analysis for a long time. You and I have been talking about this off and on for a long time. After all of this work that you've done and others writing about this have done, is mediation analysis now expected in a grant application to evaluate an intervention, for example, an NIH grant application? Are reviewers inclined to penalize applications that ignore mediation analysis?
What a great question. I mean, I think yes, and I think maybe the simplest, most practical answer is that you get more information. These studies are very expensive. Why not measure mediators and moderators as well, and to extract the most information? And I know, like the Science of Behavior Change group expect mediation, and it makes sense to try to understand why. The primary focus of any intervention, of course, is the intervention effect, but there's more information there, and you can test theory. And I mean, it can be shown also that the test for mediation can have more power than the overall effect of X on Y. So it's even relevant from a statistical power perspective. So, I mean, of course, I'm in favor of having a mediation analysis in all these grant applications.
So I understand that, but based on your own experience and your conversations with others, are the NIH reviewers looking for it when they review grant applications?
I think they could look for it more. But I guess the groups that I hang out with, I guess the groups that I hang out with often, they're doing mediation already. So we're convinced it's important. Yeah, I mean, You've mentioned the Science of Behavior Change project a couple of times in your comments today. We had a presentation from that group at the Prevention Research Coordinating Committee earlier this month, so that material is all very fresh for me. Corinna Davidson was giving that talk, very interesting, and they cited your work on mediation, obviously. Some questions from our audience. Is it possible for a mediator to also be a confounder and or a collider? And if so, is there a way to address that? Yeah, the short answer, I think the way to address these things is to think hard about them. And I find it helpful also to try to generate data consistent with that. I mean, the answer, I think, is yes. But I think it's important to have applied examples of these things and also to potentially generate data that suggests that it has both of those. I believe there's a paper by Sander Greenland where he has a collider that's both a collider and a confounder. I forget that citation, but so I mean that's one of those questions that's hard to answer quickly.
Yeah. How do you determine if the true causal distribution is linear and make that assumption for mediation analysis?
Do you have any easy questions?
I'm sharing the questions that I'm getting from the audience.
No, they're good questions. I mean, I think all these things is, and mediation is a program of research. So to try to understand the true, like whether it's linear, I think linear, works for lots of situations. Right, I think it's a program of research where you look at maybe different values of that linear effect, and it's worth it off. Yeah. So this one may be more a gentler question. What's the difference between direct effect and total effect? Right. Yeah, that often is confused. I think those of us in the mediation literature would prefer that the direct effect is the relation between X and Y that's not mediated, where the total effect is the overall effect of X on Y, both the direct effect and the mediated effect. So, what software is available that implements modern mediation analysis? Do we need special software? Can we just use regular linear regression or mixed model regression programs? We can. We just had a paper accepted for publication that reviews the causal inference software that I can send to people who ask for it. SAS has a Causal Med that estimates these single mediator model methods. That's available right now on SAS. And then M+, has these causal estimators as well as ways to handle missing data and longitudinal models and so on. And those are described in that paper. That brings me to an earlier question, which I had skipped over initially. How can investigators learn more about how to do this and how to use this software? Your book is out there. I think you're working on a second edition. There probably are workshops and summer courses and things like that. Do you have? Can you offer any recommendations? Right. There are some. It's an interesting challenge, though. It seems like the modern causal stuff is maybe in a different area than prevention. I mean, it could be, and I can send some information on that. I know that I forget his name. There's that group. Let's see. I think Felix Ewert, and I know that Tyler Vanderweel gave some workshops. That's a really good question, and that's really how you get these things disseminated, isn't it? Is with workshops. And we gave one at SPR, I guess, a year ago, and expect to do one again as well at the Society for Prevention Research Conference. That's a good question. But, I mean, most of it is in books, and a lot of it is brand new, so it's not as well developed, some of these causal methods. But then, Tyler Vanderweel's book and the Hong book are good places to start to learn about this. And I'm hoping that my book kind of is in between the traditional and the causal methods and tries to gently describe some of these things.
In your experience, how well are the assumptions that underlie these methods usually met, and are there ways to test these assumptions?
Right. Those are all. The effects as randomized, those first two are good. There's if for things like confounding of M to Y, even though you've randomized, you can't satisfy that. You can do a sensitivity analysis. There's several approaches to that would give you an idea of how big the confounder would have to be to make the mediated effect go away. And that post-treatment confounder, there are some methods proposed, like a G-estimation method, another method that's called interventional analogs to deal with that problem. So there's definitely some progress on that. Like, and practically for a real researcher, I get the idea is, I think, to measure as many of those potential confounders as you can in your research study and include them in the analysis as covariates.
A question of a different sort. What about missing data? Most of the studies that we do end up having some missing data. How does missing data play in mediation analyses? Right.
Yeah, that's, there's several papers on that, and we have a couple that uses a Bayesian approach. It allows you to do Bayesian mediation analysis and missing data, right? Because sort of Bayesian methods are part of missing data analysis. As far as I can tell, it has the same effects on this stuff as it does in any other regression equation. And actually, David, I think we're about the same age. It's sort of miraculous, the change in missing data analysis methods from when I started, when there were none, to now where programs like M+ automatically do, FIML and other methods. So missing data is as important here as it is in any analysis. But there are strategies to deal with it.
What is the relationship of the approach that you've been describing to mediation to this questioner is asking about Hayes mediation, Hayes?
Yeah, the traditional analysis is the same as the same regression method that Andrew Hayes and Chris Preacher work on as well.
Okay. So, and how is your material related to moderation and moderated mediation?
Right. I only had so much time today, and I thought I'd focus on this one issue, this correspondence. It's fascinating, really, in the causal inference literature. For them, the XM interactions that's sort of incorporated as part of the analysis. But then they have this additional thing that traditional doesn't have, and I describe it in that paper. They will test whether the total natural indirect effect is equal to the pure natural indirect effect, which is a test of whether the mediated effects in treatment control are the same as a way that's like a moderated mediation effect. Presumably, these causal effects could be looked at by subgroup, let's say for males and females, and you could test hypotheses across those two. The Causal Med program in SAS will allow you to compute each of these estimators at different values of covariates. So you could use that to get an idea, let's say, of what the natural indirect effect was for someone at a certain SES or so on. So there's progress there.
Is there a relationship between the causal estimates and predicted marginals?
I don't know what that means.
I wasn't quite certain either. I was hoping it might make sense to you, but I wasn't familiar with it. The questioner may send me a follow-up, and I can come back to it. In general, the mediated effect will nullify the association between treatment and outcome. Will assumptions change if the mediated effect is negative, such that the natural direct effect is larger than the total effect rather than reduced.
Right. All those rules about signs, these methods will apply. The methods don't care what sign the things are, but it'll all add up. It'll all work, whether the mediator, whether some effects are negative or positive, whether it's, for example, suppression and so on, or inconsistent mediation, it all works. I'm not sure that's answering the question, but.
We have someone inquiring about specific software. You mentioned SAS and M+. Are you familiar with whether Stata supports these kinds of methods?
Yes, Stata has a program called Paramed that will do this. There's a program called MedFlex by Van Steelant and colleagues. I'm blocking the name of the person who wrote that program. And then Kazuki Amai has some very usable R programs with nice plots that'll handle multiple mediators and also multiple group stuff. Amai is at Harvard University now.
Mm-hmm.
And
how about SPSS?
I'll remain silent. No, I don't know of anything that SPSS is doing in this regard.
Okay. What would be your, this one may be too technical to try to do as a question, but I will try. What would be your interpretation if neither AB nor C prime are significant, but C is significant?
Well, I guess I'd conclude that there was a treatment effect, but it's not mediated. A lot of these funny things can happen with small sample sizes. Usually people ask, what if C is 0 and AB is significant and C prime is significant? That can definitely happen. Would be an inconsistent mediation model. I have a paper from 2000 that describes some of those models that might help with answering that question.
Great.
And I think
I
sent a list.
Go ahead, David. Sorry.
Yeah, I'm sorry. I sent a list of references, both ones that I mentioned here, and then also other references on mediation. If people are interested, they can send me an email.
If you send any of those materials to us, we will post them next week with the other materials related to the webinar.
Okay.
You could send a list of references. You could send the citation for the paper where you're talking about different kinds of software. Any of those kinds of things, we'll post them.
Okay. Yeah, I already sent the list of references, but I'll send extra stuff.
Okay. We will also post the slides. Several people have been asking about that, and the slides will be posted, and a recording of the webinar will be posted. So if people want to watch portions of this again, they're able to do that. As a last question, could you cite a situation where findings from a mediation analysis change the message coming out of the study in ways that improve public health?
Right. Yeah, that's a great question. Like I said, there are times where the test for mediation will have more power. So if you have really strong theory, you could test that mediation theory and find that that's, inconsistent with chance when the overall relationship. I guess from my argument is that whenever you have an intervention study, whether it's significant or not, mediation analysis is critical because it gives you information on whether that action theory didn't work, like whether your manipulation failed to change the mediator, and also whether the conceptual theory didn't work. So you can gain insight into intervention. In fact, if there's not an overall intervention effect, I think that's definitely when you do mediation analysis to try to understand what happened.
David, I want to thank you very much for your presentation. We're approaching the top of the hour, so I'm going to turn things back over to Marie.
Okay, thank you.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. As I mentioned at the beginning of the webinar, we will be posting the slides and a recording of today's session on our website next week. You will receive an email with a link to the recording when it is available. Thank you.